Let's look at the solution to our parity quiz. We're adding parity to our memory, which consists of 8 arrays. So now the question is, should we add parity to each row of data? And then when we read out the row into the row buffer, we check for parity and report an error. Or should we have the modules as is and just add 2 more that will hold the parity? Both approaches have exactly the same number of extra bits we are adding, but the approach of having extra modules as opposed to changing the modules is preferable for 2 reasons. One is that this way we can design these memory arrays both for unprotected and for protected memories. The protected memories will just have additional arrays, but the design of each array is the same. If we decided to add parity bits here, then depending on exactly how many parity bits we are adding for how many data bits, and whether we are having parity at all, we would need to redesign our memory array every time. The second reason why using redundancy at a coarser grain rather than finer grain tends to work better is because let's say that an array fails by reading zeros for the entire row. This is not such a far-fetched error. In that case, what we have is if we have the parity bits added to each row, the row still has correct parity. So a single failure, for example, in the row decoder, will just read the wrong row. It still has the right parity. If, however, we separate the modules with the parity, then each of the modules will operate on its own. So the error of a row decoder here will cause this bit now to be wrong in every 8-bit word we read. But if these other arrays are still working correctly, then we can still detect that because the parity is somewhere else. So this is kind of similar to doing geographical distribution of our computers for redundancy. Pretty much, the further away the protection bits are, the more likely they will protect us against large failures in any single component.